Okay, so I hope everyone who's watching this is doing well. We're going to do the USACO Silver Contest from Open 2022. So let me share my screen real quick, and we'll get started with the contest. So I have not seen these problems. We're going to get started. USACO Open tends to be harder, so there's, we're given an extra hour. It might be a harder contest than usual. Let's get started. So the first thing we're going to do is we're going to try to read all of the problems. Oh, big enough. Okay, so we'll start with visited or visits. Okay, so we'll give you a couple minutes to read this if you haven't already, and I'll take the chance to read it. Okay, so hopefully you guys had a chance to read it. So we have some set of cows or bovine buddies, I don't know. There's n of them up to 10 to the 5, and each of them have another buddy that they will visit. And so they were asked to process the cows in an order such that, okay, so you only get the values that each cow will output the VPI moves, but only if the one they're pointing to or that the buddy has not already been processed. So every edge that goes forward in this permutation counts for points, but every edge that goes backwards doesn't. So I don't know exactly how to solve this. Start by writing something out. So this is visits. Okay, so one thing, this seems well, to visualize as a graph. So we can start by drawing the sample input. So this will be the sample. And try to see if we can investigate the sample. So we're given 4 cows. So we can draw in 1, 2, 3, 4. So 2 points or 1 points to 2. So I'm just drawing this on the other screen. 1 points to 2, 2 points to 3. We can write their values as well. 3 points to 4 and 4 points to 1. So they form one big cycle. So in this case, of course, the maximum moves available is 100, but the answer is 90. So that means we can't get 10 moves. Because no matter how we order these four, one edge is going to go backwards, right? So you can pick 3 of the edges to go forward. So you could do like, I guess you want one to be the one that points backwards. So you would do like 2, 3, 4, 1. So the 1 is the only backwards edge. So since it's like a single cycle, you just remove the largest or the smallest node in the cycle and count the rest of the cycle. The thing is, this graph may not be just disjoint cycles. Like I can imagine you might have graphs that look like, the out degrees are always 1, right? So we know because every cow points to another cow. But we could have like this, right? And of course, these ones are free, as in there's no reason not to take them earlier. So one observation, take all cows with in degree 0 whenever possible. But then you're not necessarily left with like, wait, are you? What are you? I think we should think about what when we remove all in degree 0 cows. Yeah, I feel like we can think about this. I do want to read the other problems, so I think we'll switch to one of the other problems and see what we can think. Because once you remove, well, I guess once you remove the ones that all have in degree 0, all of them have at least in degree 1, all of them have at least out degree 1. There's exactly n edges, which means everyone has to have in degree 1 as well. That should split you up into disjoint cycles, I think. We'll come back to that. Okay, subset equality. This is problem 2. So we'll take a couple minutes to read this. I'll give you a chance to read it if you haven't already, and I'll take the time to read it. Okay, so hopefully you guys had a chance to read this. We're given 2 strings, and we're given a set of queries. And so one thing, the strings have an alphabet that's restricted to just A through R, which is that's 18 letters. Okay. So the bounds we have, we're given length 10 to the 5, 10 to the 5 queries, and we have 18 letters in the alphabet. we can see on the sample like AA and AA are equal, but AC, you get AAC and CAA, so it's no. ABD are fine. ABCD is not. Okay, we'll come back to that one. On the last problem. Okay, so we'll take a couple minutes to read this. If you haven't read already, feel free to read it or skip ahead. Okay, this sounds like an interesting problem. So let's okay, there's two types of queries. You can either choose two adjacent equal letters and delete them, or you can replace like a C with an OW or a WO. You can replace an O with an CW or WC and so on. Maybe it's useful to think about this one. So this is cow operations. We have two queries. You make them a string. You can either delete any CCOOWW or O goes to CW/WC, C goes to O, W/WO, and W goes to CO/OC. So you can apply these like replace and delete rules to characters in the string. Well, I guess let's try an example. So the sample is cow possible? Because that's the sample input. So when I get to a single C, what can we do? We can replace, you can replace the O and you can get like CCWW. And that, well, you can delete yourself into empty string. That's not, that doesn't work. So let's look at this. Is this actually possible? 1, 3. So this is not possible. So how would you prove this is not possible? I guess one thing I want to do as a good trick for these kind of problems is look for invariants that don't change. After operations. Thing is, I mean, the size will change you could look at like parities, like maybe parities of number C's, O's, and W's, but this can change, right? It's no good. Okay, so what's the case that does work? I guess OW can go to, because here you could do like CWW and then you get it to work, right? Because then you can just go to C. So this works. What about O? O does not work. I don't think that works. Because you're forced to delete, or you can do like O WC do OOCC, but it seems like you're stuck, but I don't really know why. So OW and WO both work. OO does not work. CC, I mean, probably doesn't work, but why? Well, you either delete it, you get nothing, or you make an operation, you end up with cow without loss of generality, like OWC, WOC, like they're all just the same as the sample. So we know this one's not possible because you can only go to like OWC or like COW or just empty string. So you're just stuck. WW is the same as OO, but like OC. We can know that from the sample. Which ones in the sample actually work? It's just C and OW. Okay, so from the sample, if we're looking at like pairs, we know that OW works, WO works. If we're looking at ones that are up to length 2, C will always work. CC should not work. OO shouldn't work. WW shouldn't work. So I think maybe up to length 2, these are it, because the sample also tells us like OC or WC don't work. And it's symmetric, so you can flip them. Okay, so what do you need to add if you have like CCOW? This works because you can just get OW. Maybe I should just play around with some examples. Let's keep messing with this. I like this problem. I think I'm gonna think about this. Of course, we have ideas for the first problem, and I didn't really thought much about the second. So, but I think I like this problem. I think it's worth thinking about this one for now. We'll switch when we get stuck. Okay, so in this case, COW you could do O. I guess you could take something like, okay, ignore that. You could take something like OW, go to, I guess you can't go that exactly, but WCCO. So you can kind of like combine operations to flip two characters and insert CC or any other double letter. Those are deletable. So I guess you can actually go from OW to WO. So this gives us one observation. Can arbitrarily flip any two characters in the string. So even though it's not one of the two operations we were given, we know that this operation can be formed by applying two of the second operation, one of the first operation. And so we can now assume that this is an operation we have. But this implies we can rewrite the string in any order. That's actually a very powerful solution. So now we can look at I mean, if there's like an even number of O's and an even number of W's, you can just get rid of all of them. So, odd number of C's, even O's slash W's always works because you can just delete all the O's, delete all the W's, and delete everything but the last C. But is that always true? I don't know. And of course, that's not the only cases that could work. So if we go back here, is there another thing we do here? Is W with OC. We can be left with C, but that's not necessarily what we want. I just want to see what else we can do. We can take a single letter. We can go from like O to WC and then OCC. This is another operation we could do. I think this, another observation that we can see can arbitrarily insert a double letter after any letter, as long as the string is non-empty after or before. So we can do something like O to O, no, to W's, C to OCC. And you could, of course, instead done CCO, CW. And so without optionality, we can arbitrarily insert double letters. So that does make me again think of parity. Because now we can actually increase, if we, as long as we have a, we can always reorder them however we want. So we can make the string look however we want. And we can arbitrarily change the actual number of C's by an even amount, number of O's and number of W's by an even amount. So that's actually a lot of control using these operations we built. So okay, so let's think about this. So we want to, I think only parity is going to matter, right? And the way we can prove this is that two solutions with the same parity either both work or both don't work. And the way we can prove that is, so assume fixed parity over two strings. They have the same even oddness of the number of C's, even oddness of, so of O's and of W's. We can change number of C, O, W in first string to match the second. And we can also reorder the string to match the second. So we can transform, so let's say it's like A and B, we can transform A into B or B into A because it's symmetric, right? So if you can transform one into the other and the other into one, you can't have them have different solutions. If one of them works, then you can either just transform it that one and do the same solution or vice versa. So they either both are yes or both are no. And so this proves only need to know parity to know solution. Which makes this actually very easy because the number of possible parities is 2 cubed, right? So in this case, we can actually just enumerate them, right? So if you have 0, 0, 0, well, that corresponds to the empty string, which I guess you don't worry about the empty string because you can't always transform the empty string. Okay, well, the empty string doesn't work. But let's say it's not empty, then you can actually arbitrarily make it any string but the empty string. So it's like special case empty string. This proof right here does assume these strings are non-zero in length. So non-empty. This corresponds to this corresponds to like OO, for example, which that's not OO, which we know does not work. I think, at least I believe it doesn't work. So this should be no, and then it's no even if it's empty, right? Because the empty string is also a no, so it's not actually a special case. Also no though. Okay, so 0, 0, 1, where let's say it's a W, right? So let's say this is like the number of C's, O's, and W's. So this corresponds to just W, which the sample tells us is no, which we saw in the sample, which also is the same as this, because this is also no. W and 0 are symmetric. But you have 1, 0, 0. This is this works, right? That's our first yes. Then we can get 1, 0, 1, which is CO or CW, which we saw in the sample does not work. Same with CO, does not work. Finally, we can get 0, 1, 1, and we know this one does work because that was in the sample. So we're actually really using the sample to actually prove, like, I didn't really prove some of these cases, but I'm mostly basing off the sample because it's easy to just use the sample if we already know the answer for this case. We only know we just need the answers to the 8 cases, and if these 8 cases are wrong, then you can always fix it. But this works, and then 1, 1, 1. That is just cow, and we saw that in the sample. That does not work. So that's equivalent to cow. So in this case, we have a table of our answers. So the idea, use a pre-computed table of answers based on parities. And then we need to answer 10 to the 5 queries. So we can use a prefix sum to compute parities. Okay, this is actually probably one we can implement. This idea seems like it'll work. And we've improved it so. And in USACO contests, like, although you don't need to prove them for this kind of problem, it actually seems very natural to prove it, right? Because if you don't prove it, you might be kind of guessing checking. Maybe you think parity works and you're just going to try it and be like, okay. But I don't think it's necessarily obvious, and it's worthwhile to take your time on a USACO contest because coding something that doesn't work is just a waste of your time. The extra 5 minutes to prove it is probably not a waste of time. Especially with given how long USACO contests are, you have 5 hours. So Okay, so we can start implementing this. This is bigger. Okay. Okay. So we need to take an input. We need to store a string, Q, the number of queries. We need to store, and we also want to store the prefix sum. So we're going to want int max length of the string, 2 times 10 to the 5, and there are 3 characters. So we'll go with COW. Start by taking input. Process the queries. So we need to first pre-compute all prefix sums. So prefix sums 0, 0 should be 0, or for any of these, right? They should be 0, but that will be default initialized. So you don't need to do that. And so what we want to do is we want to loop over so the same prefix sum, add 1 if new character. If s of I equals c, prefix sums I plus 1, 0 plus plus. We can just copy this code. We do the same thing here, just copy this. This is standard prefix sum. Okay, so we want to take in the inputs, int r endpoints. We could decrement these to actually have them be 0 index, but I'm gonna keep the 1 index so we can actually just query for the so int c count equals. We'll use our prefix sums array of r of 0 minus prefix sums l minus 1 of 0. Make sure to select 1 so that we don't include. We don't delete the left endpoint. It's any inclusive up to. We'll do the same thing. Okay, so if we remember our cases, I think 2 cases we have that work are either them all being 1 or if just C is 1. So we'll actually just okay. So if C count equals 1 and if O count W count 0. So this is like the one of the 2 cases that work. And The other case is if C count equals 1, O count. Works, we'll output a yes. Okay, so this is not a lot of code. I think the hard part of this problem is probably just coming up with these cases. So I'm gonna try submitting this after we test it real quick. And that is not correct. Oh, sorry, the case is not when they're all one. I misread my. This is the case that works, not the case with all three. Okay, so matches the sample. Seems reasonable to try submitting it. Okay, I think hopefully didn't forget anything. I feel like this should work. I feel pretty confident. Of course, it runs very fast. Oh, actually, I wonder why. I mean, 1 second feels a little high for a lot of problems, but yeah, doesn't matter. I mean, you're given 2 seconds, so it's still well within the time limit. But yeah, okay, so that worked. I think the hard part of the problem is just take the time to investigate the samples. Like, it's not obvious at all looking at this, like that these queries mean you only have to check the parity. But once you know that, it's very easy to solve, right? So the 2 queries that we figured out we could build out of these, we tried to see what can we do with what we're given. And eventually we stumbled across 2 things and we're like, oh, those work. And we just went with it. So it's definitely a problem where like taking the time to investigate on paper and prove things is worth your time. Yeah, we're done with one of the problems. I guess we can come back to visits. Okay, so we did think of that as a graph. And so the one observation we already have is we want to always process in degree 0 nodes first, or whenever possible. Because it's possible as you go, you'll introduce them. Although I guess once we remove, so the idea is after all degree in degree 0 nodes, this implies that remaining graph is disjoint cycles. The way you can prove this, there are, if you have a remaining, n nodes remaining, which means you have n edges remaining, because every time you remove a degree 0 node, you remove an edge with it. The out degrees are all 1. So, but the in degrees are all at least 1. but there's only n total edges, and an edge is only incident to one node, which means, the in degree always is 1. So you remove the ones that point in with degree 0, and you're left with cycles. So once you're left with cycles, as we saw in the sample is a cycle. It's just this 4 cycle. So in this case, we want to remove one node. And so you must remove one node, right? Like the value of one node. So one of these nodes will never get processed, but we can put this cycle in an order such that only one edge is going backwards in the permutation. So the idea take the smallest node from this cycle and exclude the value. In this case, there's 2 steps to this. One, we'll first greedily remove all the nodes that have in degree 0. So step 1, so the solution ends up being kind of greedy, right? We proved, or we at least convinced ourselves that, there's no reason not to remove the ones that in degree 0, because you will get the points for free and not affect other nodes, because no other node depends on you. So it's free, like points to add the maximum. So step 1, this is sort of a greedy solution. Step 1, remove all in degree 0 nodes. But we have to do this using a queue. So use a queue to do this, because removing a node reveals more in degree 0 nodes, because it will decrease the degree of the node that it points to. So we'll do this step, and then step 2, remove one node from all remaining cycles. Okay, so this is probably something we can implement. I think we'll start with it. And then we come back and we can think about B. Of course, if you prefer to implement later and keep thinking about the problems first, it depends on what you prefer. You can always keep the problems that you're not thinking about in the back of your mind while you're coding, stuff like that. It's definitely up to you how you want to prioritize. Should you implement right away? Because you have a lot of time during the contest. Later if you want. We'll start with our template. We're going to take an input and cows. So int buddy of each of the cows. So max n equals because then we also want the value. How many times each cow will move. So we're going to take in all of these, take in cows, and then for each cow. So I will 0 index buddy of I times minus. Just make this easier. So we're gonna have 2 steps. Step 1, use a queue nodes. We're gonna need that Q. We can just use Q in C++, Q in Q. We need to initialize the Q with all current degree 0 nodes. So the thing is, we're gonna need to keep track of the n degree. So as we process nodes here, we need to keep track of the n degree. So we need to initialize degrees. We do this by here the n degree of a of I, or by buddy of I. So we'll loop over all the current nodes. If n degree I equals 0, we're gonna add it to the queue. So push I. So now while not q.empty, pick up the front node, pop off the front node. So in this case, it's not a process. We do need to keep track of our answer. It needs to be a long, I think. Yeah, so make sure to read the small things in the problem. It does say we need to use 64-bit ints because you could get 10 to the 9 times 10 to the 5, and it would be around 10 to the 14th. Or at least you can get almost all of them. So we need to update our answer. Answer plus equals v of x, or sorry, value of x. I need to update it over 0.2. So the n degree buddy of x minus. So add to q if now 0. If we now have 0 n degree, we can just add it to the q. Okay. So now we need step 2, 1 node from all discharge cycles. So you could like just remove 1 node process cycle, or like remove the nodes and like order small. I think we do need to know which ones are processed. So here we want to actually done of x equals true. We need to find all the cycles, so we can do over all the nodes, and if not done of I, we found a cycle. We need to, so we want to loop over the cycle. So we'll use a do while loop. Just make the first step not terminate. So cur equals buddy of first. Reverse. Okay, so in this case, yeah. Okay. So we can keep track of the smallest value we see as we go. Even if we don't include the last case, that's back at the start, so it doesn't matter that this is before this. You can do it after that too. So in this case, we also want to keep track of the total sum. It won't double count the last node. Ants plus equals cycle sum, and then ants minus equals smallest value. The smallest node. And then we can output answer. Okay, so that does what, at least my first estimation. Let's see if it compiles. It does. Let's try running it. Oh, we forgot to mark these as being done. So it's done, occur equals true. Double process. We do get 90. Again, with USACO, like there's really no reason not to submit. We could try to generate test cases, and for some contests that's better, but here we're not really too worried. So we can just submit and see how it goes. Hopefully this works. It does pass the sample at least. So there are some test cases. So the first one, I guess that ensures in degrees are all one. So it's a single cycle, I think. I guess we have to wait for the grade. So we do pass those cases. We do pass everything. Okay. So for this problem, like we found a greedy solution, but really the important thing was try thinking about this as a graph problem, even though they didn't explicitly phrase it as a graph. Once you start visualizing the graph, it can really help you kind of notice patterns. And once you learn about cycles and degrees, which are things you would think about with graphs, you can probably come up with a solution. This one turned out to not be too tricky. But like when you read the problem, it's not necessarily obvious how to solve it right away. Okay, so we have one more problem. Subset equality. Okay. So this is subset equality. Okay, so one observation we can make. Or one, if we think about like what the naive solution is, each query can be processed in O of the length of the string, we'll just call that L, where L is the length of S. Max length of S of T. Because we can just use can two pointers to loop over both strings. But the thing is, this would give us a total runtime of O of Q L, which is, approximately like 10 to the 10, which is just too slow. So we know we need something linear or log linear, or maybe a factor of the alphabet, right? The alphabet size only 18. And if they picked 18 instead of 26, maybe they meant it to not be too large because 26 would have timed it or something. So we might expect a factor for alphabet size. So one observation I would notice is if any letter has a different count in S and T, then this implies any query, including this letter, cannot ever work. So in this case, that doesn't hold for any of them, but if that was true, then you can immediately rule out those. Obviously, that doesn't help us solve it, but that's something to notice. So in total, there are 2 to the 18 possible, or 2 to the 18 possible queries for whether you have subsets of 18 letters in the alphabet. Okay. So let's look one of the samples that fails. If you have like, let's mess around with the sample. We have the strings. I'm writing them down real quick. In this case, we have the sample A, C, A, B, D, and A, B, C, D. So the ones that fail are A, C, and A, B, D, C, D. But if we know AC fails, so one observation, if a query already fails, adding more letters cannot make it succeed. So it's kind of got this like monotonicity property. So, if you have like a query Q, which fails, and you add letters, you add a set of S letters. You'd be left with two strings if you want to prove that this works. You give me Q union S gives two strings. But if you remove the characters from S, so assume union S works as a query, then you would get the two same strings. You remove characters from same strings, and you would have to be left with the same string because that you did the same operation to the same strings, means resulting strings are equal, but this contradicts that Q fails. So adding more characters cannot make Q succeed. So knowing that AC fails implies a BC, ACD, and ABCD all must fail as well. Okay, so that's one observation on the sample. I guess another thing let's consider which fails. So, S after removing the letters becomes some S prime. T after removing letters becomes some T prime. We know that S prime not equal to T prime. So consider the first character where they differ. Well, of course, they could be different lengths. So assume, well, if they're different lengths, they're going to fail. We can just assume that case. So we can already assume, because we showed earlier, we don't actually need to worry about the lengths because we can actually ignore characters that mess with the lengths, like different arrays and a string. There's no reason to consider anything else after that. We look at the first different character. Let's say that's CS in S prime and CT in T prime. If we look at the query, just CS and CT as a set. So only a 2-character query. In this case, CS and CT must fail as well. We can prove this because if you take just CS and CT, maybe you remove some characters from the prefix, right? So you had the prefix may shrink up to CS, CT position. Let's just say at index I. So S prime to I equals T prime up to I. But if you remove the characters, the prefixes shrink, but they shrink by the same amount. They shrink in the same way. So, but CS will still not be equal to CT at the same index I. Same. It's shifted over. So hopefully you can imagine. I didn't really notate this very well. But we know that if there's some character that differ, those two characters, whichever characters differ, makes the failing query. So the idea that I have is one, check if counts in query are valid. So we can ignore already impossible characters. So maybe A on its own doesn't work, C on its own doesn't work, something like that. And then step 2, try all 2 character queries. If a query fails, we only need to check if it contains a failing 2 character query. Because if it does fail, it will, and if it doesn't fail, it can't, because of the monoticity. So we proved that these are correct, and we can continue. So again, we took our time to prove it. It's probably worth it. Here, our total runtime would end up being, depending on how we do this, but 1, we can do the pre-processing, and we'll get like O of L times the alphabet squared, sigma squared. Plus for each query, we can also loop over all pairs in the query, which is also sigma squared. So that's probably why they made the alphabet be 18. So sigma is less than 18. So yeah, that should pass. It might be a little tight on the time limit, but it should pass. Okay, so let's start by trying to implement that. So let's start writing a simple template. So we're going to want to take an input. We're going to want to pre-compute which characters fail on their own. Pre-compute which pairs of characters fail. And we'll process. There are 18 possible characters. We'll do process. And then we want pair fail sig. So these are the 2 strings. We're going to keep track of length or frequencies. So we'll keep track of an int. I'll pick up here. So int count s, or yeah, count s sig, count t. Pair. Okay, so we will loop over and we'll keep track of the counts. We'll count frequencies. Best. We want to update count s of I minus a. So we'll put it the index between 0 and 18 instead of using the character, and we'll plus plus. We'll do the same thing for t. Here. Okay, so for all possible characters, if count s of I not equal to count t of I, then we know that this character has to fail. So this would be We're going to try all possible pairs for int I equals 0, I less than sig I plus plus. We only need to try start j equals I plus 1 because we only care about the unordered pairs. Okay. So we can check if this works. We need to actually loop over the string. So remember that naive algorithm we had? Well, that's actually basically what we're doing. We're just doing it on a restricted set of possible queries, which is how we got at the solution. So we want to use 2 pointers. We'll keep track of the variable that this works. And then if it doesn't work, we'll make sure we mark it as fail. So int p1 equals 0, p2 equals 0. So there are 2 pointers, and then while true. Or skip over characters. So while p1 less than s dot size and s of p1 not equal to I and s of p2 minus a. So this case, yes, we would increment p1. We'll do the same thing for 2, 2, so if too long, break, if p1 is greater than equal to they're both too long, then that's fine. So this is when we're done. We process both strings. However, if p1 greater than s dot size, but the other one's not, then in this case we know it fails. We do the same thing for the other case. Okay, so now we need to check if characters differ. So if s of p1 not equal to t of p2, we know these are within range, then this also fails and we just break. Otherwise, we could do p1 plus plus, p2 plus plus. Okay, so I think this does what we want. This is how you would implement the naive algorithm if you're going to do it anyway. Okay, so that now we just need to process the queries. So input query. So our query is a string q. This is the letters. Check. So see if this works. We'll start off as true. For if j equals 0, j less than size, j plus plus. If q of j minus a is a failing character, which we already pre-computed, then this doesn't work. Now we want to check pair failing characters. So we want to try all possible pairs. We can actually just loop starting k equals j plus 1 because we only want ones that are increasing order. like unordered pairs, and also we are told they'll be in sorted order. Not that we couldn't fix that if it wasn't, but it's nice that it is. So if pair fail, Q of J minus A, Q of K minus A, false, then we can break. Actually, well, I'll add that breaks. Now we can output query answer. So if works, we can see out yes. Otherwise, we can see out no. And we can output a new line. Doesn't terminate. And we do this while true loop here. Likely place for instant loop. Should break whenever you exceed the lengths, but maybe my second. Right now, I and J or whatever we should. What's the query word processing? That's not at all. Why is I growing so big? Oh, that's because we made a typo. It does pass the sample, and again, because I believe we proved this correctly, and we have our proof right here, that a query which fails will at least fail on 2 of the characters in the query, assuming that we have the same lengths. So we should get this runtime. Hopefully it passes. I mean, the time limit could be a little tight, but 18 squared, it's quite a large constant. But we'll see how it does. Okay, and then you pass. So yeah, this problem, this contest didn't go too badly. For a lot of these, like, I would definitely recommend not rushing into coding them. I mean, some of these, like, you don't even know what you'd code if you rushed into it. Like, take the time to think about cases on paper. Like, both problem 2 and 3, like, you kind of have to prove something in order to convince yourself your solution is correct, right? It's not at all obvious to try that. Here, we needed to prove that these queries actually preserve, like, we don't preserve parities, but parities are the only factor you care about in determining whether it's yes or no. So the invariant was not obvious there, but when you mess around with it, you're able to prove, there are certain queries you can construct with these. But same with number 2, like obviously we can't try every single query. We have, the naive algorithm would be too slow. But if you take the time to mess around with examples and try to prove, that ABC will fail, even if AC fails, and so on. And so try messing around the sample. Always make sure you take the time to investigate them. And number 1, this one, you really just had to think of it as a graph and try to realize a couple of greedy properties in order to find the greedy solution. So it wasn't too hard for us to prove this, but again, we also did sort of prove that was correct. So I hope this content went well for you guys. I hope this video helps you get an idea of what it's like in a contest, how you might want to prioritize your time, or where you would want, do I rush in implementing, or should you wait? Like what kind of, how do you come up with observations? Because I hadn't seen these problems before, and you get to see what it took to come up with the observations for these problems. So I hope this helped you guys. I hope you guys had a good contest as well, if you participated. And yeah, that's all I have for today. I hope you enjoyed this. Thanks for watching.